All right, the next, I guess, logical topic to go into now that we've talked about gases is to talk about heat. Okay, so this next unit is thermochemistry. It is chapter 5 in your textbook. Obviously, there's some heat being generated there. That's the Hindenburg disaster, if you don't know about it already. Now, in this unit, there is going to be a lot of weird terms and units, some of which you've heard before and some you might not have. But the thing to remember is conversion factors or dimensional analysis, whatever you want to call it, is your friend. Okay, you don't. What I'm going to try to show you with this silly example here made up out of Dr. Seuss words is that you don't, not that I'm encouraging this, but you don't even have to know what you're doing to get the right answer. I know I've gotten the right answer many a times when I had no clue what was going on. You simply divide by the unit you want to cancel and you'll get there. So I want you to pause the video and try this problem. It's silly, but it's mathematically identical to a problem we are going to do in this unit, and it hopefully build your confidence a little bit that in spite of all the terms and units and everything, you can do this. We're just multiplying and dividing, okay? So a fufu worth 2.37 wockets eats 127 zazits. How many sneedles will it increase by if its Diffendufer ratio is 10.27 zazits per sneedle per wocket? Okay, so that's 10.27 zazits on top divided by sneedles times wockets. Okay, so that's in your denominator. Oh, I suck at that. It's on bottom, whatever that word is. So write down what you're given, what you're asked for, set this up as a fraction because you're going to use it as a conversion factor. Remember, you can flip it upside down if needed. So just pause and try it. All right, now on to the thick of things here. Energy is simply the capacity to do work. There's all different kinds of energy. We're going to focus on thermal energy in this unit. Thermal energy is the energy associated with the random motion of atoms and molecules. So the more thermal energy, the more they move, okay? And we talked about that in the gas unit. We called it kinetic energy, the energy of movement. All right, chemical energy is going to come up as well. Chemical energy is the energy stored within the bonds of chemical substances. Okay, so you can absorb or release energy by breaking and forming chemical bonds. All right, nuclear energy we won't get into. That's one of my favorites, though. That's the energy stored within the nucleus of the atom. Electrical energy we'll talk about more later. It's the energy associated with the flow of electrons. And then there's potential energy. Chemical energy is really a form of potential energy. It's the energy available by virtue of an object's position or stored in the chemical bonds. Oh, the thing about all these is that they can be converted to one another. Nuclear energy is converted to thermal energy, which is converted to electrical energy, and that's where that's how nuclear power plants produce electricity. All these can be converted. Remember, energy cannot be created or destroyed. It can only change forms. So this is basically a rough outline of the chapter. We're going to talk about energy in general, how that applies to the first law of thermodynamics. Then we're going to get into enthalpy and calorimetry. Told you, lots of weird words. And then from that, we'll branch out into Hess's law and enthalpy of formation calculations. You looking forward to it? This unit's going to be a little bit tougher than the gas law unit. All right, so first off, just the nature of energy. Thermodynamics is the study of energy and its transformation. So if you're taking physics, or if you do take physics, you'll likely cover a unit on energy as well. Thermochemistry is what we're going to focus on, the study of the relationships between chemical reactions and energy changes involving heat. So just some basic definitions we need to know. The law of conservation of energy simply states that the energy of the universe is constant. There's only so much energy here. It just keeps changing forms. So energy is only converted. It's never created or destroyed, except in a nuclear reaction. And don't worry about that. We're doing chemistry, not nuclear reactions. All right. Energy is simply the capacity to do work or transfer heat. Work, then, is the energy used to cause an object with mass to move. You may not think about chemicals doing work, like hammering a nail into a board or something, but chemicals do work. Think about a gas expanding, okay? It's applying a force over a distance. It's causing, the balloon to expand. Something's moving. So chemicals most certainly can do work. All those questions in the gas law unit about the piston being moved by the gas, work was being done there. So work is simply equal to the force applied times the distance that it was applied over. Okay, that gives you the work. Now, force is just any type of push or pull exerted on an object, and we talked about how gases can produce force. That's what pressure is. But the most familiar force is the pull of gravity. That doesn't apply a whole lot with chemistry, though. Heat, then, is symbolized with the letter Q. Okay, work is W, heat is Q. You're going to see a lot of W and Q. Heat, Q, is the energy used to cause the temperature of an object to increase. So, kinetic and potential energy. Well, kinetic energy, as you know, is the energy of motion. Kinetic energy increases as velocity increases. We learned that in the last unit. The more energy the particles have, the faster they fly. The faster you drive your car, the more kinetic energy it has. And the more massive the object, the more kinetic energy. Remember, KE equals 1/2 mv squared. It's the product of the mass times the velocity squared. So the more massive, the more energy, and the faster, the more energy. So an SUV going 70 miles an hour is going to have more kinetic energy than a compact car going 70 miles an hour. And there's your formula for, there's your formula for kinetic energy. Remember, the mass has to be in kilograms when you're using this equation. All right, potential energy has its own formula. Okay, that's the energy of an object that it possesses by virtue of its position or composition, meaning chemical composition, the energy stored in the bonds. Well, if you're talking about a book on a shelf or something, the potential energy is equal to the mass in kilograms times gravity, 9.8 meters per second, times the height that it's elevated to. That gives you the potential energy. So potential energy occurs when a force is operating on an object, and that potential energy can be converted into kinetic energy. If you push the book off the shelf, that potential energy turns into kinetic energy of motion as the book falls. An example of a ball of clay dropped off a building. Okay, it had a lot of potential energy when it was up on the roof, and then that turned to kinetic energy as it fell. So, another reminder here, velocity is in meters per second. The mass has to be in kilograms for these formulas to work, and height then needs to be in meters because velocity is in meters per second. And then gravity also needs to be in this form, 9.8 meters per second squared. All right, so here the biker has potential energy, and then once he goes over the hill here, now he's got kinetic energy. Now we need to apply all this to atoms and molecules. So in chemistry, we don't study the energies of cars and bouncy balls. That's what you'll do in physics. But instead, we focus on the tiny invisible world of atoms and molecules. Gravity has very little effect on the forces between small molecules. That's why we don't discuss it much. Most of the force between atoms and molecules is due to electrical charges, meaning the positive protons and the negative electrons. Okay, gravity is not responsible for holding a nucleus together or chemical reactions. That's all about charge. So electrostatic potential energy arises from the interaction between charged particles, and that can be attraction or repulsion. Remember, opposites attract. Chemical energy is another type of potential energy that's stored in the arrangements of the atoms, meaning in the bonds. And then chemicals can also have thermal energy, okay, due to their temperature. So these are the main types of energy we're going to apply to chemicals, okay? That electrostatic, opposites attract kind of energy between the positive and negative charges, the chemical energy stored in the bonds, and then the thermal energy due to the kinetic movement of the particles. All right, so units of energy. Okay, the SI unit of energy is joules, represented with a capital letter J. Okay, hold on, kinetic energy equals 1/2 mv squared. If we plug in the units, we've got mass in kilograms, velocity squared gives us meters squared over seconds squared. So 1 kilogram times meters per second squared is a pain in the tushy to write all the time when you solve for kinetic energy. So instead, we just write J. Okay, 1 kilogram times meters squared over seconds squared is equal to a joule, 1 joule. Traditionally, we also use the unit calorie as a unit of energy. So 1 calorie, and you'll need to write this down, this comes up a lot. 1 calorie, 1 science calorie, is equal to 4.184 joules. Okay. If I'm remembering right, that's roughly the amount of energy it takes to like pick up a cheeseburger and bring it to your mouth. Okay. Not a whole lot. Now, on our food labels, we have a different kind of calorie. That's called a nutritional calorie, and it's capitalized. Okay, a nutritional calorie is 1,000 science calories, or a kilocalorie. It's KCAL, kilocal. So nutritional calorie, so if a soda, has 120 calories, each one of those is 1,000 science calories, or 4,184 joules in a nutritional calorie. All right, here's our first sample problem. What is the kinetic energy of a 28,000 pound school bus moving at 45 miles per hour? All right, we have the mass of the bus, and we have the velocity of the bus. But none of it is in the units we need. Okay, we need our mass in kilograms and our speed in meters per second, not miles per hour. So we got some preliminary work to do. First thing, take our 28,000 pounds. There's 2.2046 pounds in a kilogram. So our bus is 12,701 kilograms. Now we gotta do the same thing with our speed. 45 miles per hour. Remember, whenever it's a something per something, set it up like a fraction so you can see where you need to put stuff so they'll cancel. So first thing is 1 mile is 1.6093 kilometers. I wouldn't expect you to know that off the top of your head. And then there's 1,000 meters in a kilometer. Now I'm going to take care, right now, at this point, I have meters per hour, and I want meters per second. So in an hour, there's 3,600 seconds. So this all works out to 20-ish meters per second. Now I can plug it in to my kinetic energy equation, 1/2 times the mass times the velocity squared. Now, when you put this in your calculator, everybody's calculator is different, but the thing is, you only want to square the velocity. You don't want to square the whole dang thing, okay? So I guess I should have really put my 2 inside the parentheses, but at any rate, just make sure you're squaring only velocity. Maybe type that in first and square it, hit equals, and then multiply it by the mass and the 1/2. When you do that, try it, make sure you can do this in your calculator and actually get this. This is our answer in joules, but we really don't know all those sig figs. We only know 2 sig figs in both our numbers up here. So rounding that to 2 sig figs, I get 2,600,000 joules. Or I'll put it in kilojoules. A lot of times we're going to be, a joule is really small. So a lot of times most times really, we're going to need to put our joules in kilojoules to make it a more reasonable size number. So dividing by 1,000, I get 2,600 kilojoules as my answer. Okay, now here's more like what we're going to have to do, okay, because we don't care about school buses that much. We want to know about atoms. So what is the kinetic energy in joules of an argon atom moving with a speed of 650 meters per second? Okay, well, remember, that mass on the periodic table is the grams in a whole mole of argon, and we want just an atom of argon. So if we're talking about an atom, that mass on the table is in AMUs. So that's not cool. We need it in kilograms. So there's the conversion to get it to kilograms. Then our speed's in meters per second already, so we're good. Plug and chug. Make sure to only square the velocity, and make sure you can get this in your calculator as well. 1.4 times 10 to the negative 20th joules. I've got it round to 2 sig figs here. So this is a conversion you'll need to get from the mass on the table of just one atom in AMUs to kilograms. Okay, not a whole lot, right? We're talking about the mass of just one itty bitty atom.